All right, Weinberg, part 2. Now that we know what we're after, which is D, H, and R, and D, H, and R are the proportion or the percentages of the dominant, heterozygote, and the recessive genotypes, right? So these are really percents here, so I'll put percent signs over there. And we know that the dominants plus the heterozygotes plus the recessives equals 1 because that's everybody in the pool. And I've labeled them down here. You can see they're big A, little a, big A, big A, big A, little a, little a, little a. Those are the genetic combinations. So D is equal to homozygous dominant, okay? Now we're going to look at this as a gene pool. Now I want you to imagine it's infinite. Okay, imagine this is infinite in size. Okay, meaning there's millions and millions of individuals. And the way that Hardy and Weinberg figured you could do this is you could say, well, what would happen if each individual, right, threw a gamete out into the next generation, had 2 offspring, and in those offspring it made the same expected frequency that it already has. So it made little a. The little guys here, the homozygous, they made little a's, and the heterozygotes made 1 a, big A, 1 little a. The idea is, what is the probability if you generally pool 2 alleles? So you have to separate the alleles out and calculate their frequency. So let's do that first. And let's look at the frequency. I'm going to get rid of these guys that I made as reproductives, right? I have in this group, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals. All right, and of those 10 individuals, I have, that means there are 20 alleles. So if I want to calculate the frequency of big A is something over 20, right? And I can count them up. I just grind them up and make them independent of their organisms. So I have 1, 2, use my marker, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 big A's. So that's 10 out of 20 for big A. And the frequency of little a, we can subtract or we can count. Let's count for now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 of those. So that's 10, whoops. That's 10 out of 20 as well. And this is equal to 0.5. And this is equal to 0.5. So we know that the frequency of big A is 0.5, the frequency of little a is 0.5, so they're half and half. Now I go back in and I ask, what if we have, we're going to make some assumptions here, and assumption number 1 is going to be that you have infinite population size, and 2 is we're going to have random mating, so no one's allowed to favor anybody. 3, there's going to be no selection. So no individuals, no genotypes are favored. 4, there's going to be no mutation. Now we haven't really talked about mutation in this way, but what this basically means is that big A cannot mutate to little a. Big A can't mutate like that to little a. We're not going to let that happen. And the 5th one is there's going to be no emigration or immigration. Okay, so these are the 5 ways in which alleles can change frequencies on us in some caused way, and that's not going to happen. So we're just going to ask, if you had an infinitely large pool and you randomly recombine them, what would be the frequencies of D, H, and R given these starting frequencies? And that's really important because the way we can calculate that for the D down here, we're going to start here at D, is the probability of basically getting 2A gametes, big A gametes, out of this whole pool. So that is the probability of drawing a big A times the probability of drawing a big A out of that whole pool of gametes. The probability of drawing a big A is equal to the frequency of big A. Just like drawing a heart out of a deck of cards is 1/4 because there's 4 suits, so the frequency of hearts is equal to the probability of drawing a heart. So I'm going to simplify this to being 0.5 is the probability of drawing big A times 0.5, right, which is equal to the frequency, so that's also the frequency of big A. Now I'm going to go ahead and name this. frequency of big A is going to equal P, and the frequency of little a will be Q. Okay? So now we have two different letters to represent that. So this one is going to be the frequency of big A, which is P squared. Okay? The frequency times the frequency. I'm going to move to the recessive side over here. And the same thing is going to be true here. It is the probability of drawing a little a times the probability of drawing a little a. That's two in a row, right? Which is equal to 0.5 times 0.5 in this case, which is going to be the frequency of little a times the frequency of little a, which is going to be Q squared. Now the middle is a little bit different because there's two different ways to get a big A and a little a. You can get the probability of drawing a big A and times the probability of drawing a little a, but you could also get a little a times the probability of drawing a big A, because you can get it in two different orders: big A, little a, big A. And because of that, this probability of drawing an A is equal, A is kind of a ridiculous thing to say, right? Probability of drawing a big A is P times Q and Q times P. So since those are the same thing, this is actually 2PQ. And I'm going to bring this down here to be P squared. Okay. Now what we know is that the expected frequency of the dominant homozygote is the square of the frequency of big A. And the expected frequency of the recessive homozygote is the square of the frequency of the recessive allele. And we know that the expected frequency of the heterozygote is 2 times the frequency of big A times the frequency of little a, which is 2PQ. So these numbers here in this equation, this is the big model that everybody's excited about, but this represents the expected frequencies when there's a large population, so there's no sampling variance. The random mating occurs. There's basically nothing favoring any one genotype over any other genotype, and that's this list of conditions here. And so we'll call these the assumptions. And then it's very easy to predict these frequencies. That is the Hardy-Weinberg